Okay, it's 12 o'clock, so welcome everyone to the second installment of the second series of Polish NMR seminars. Today we have two great speakers, Sylwia Jopa as a student talk and Professor Szymon Pustelny as the main talk. And we'll start as usual with some informations. So I remind everyone about best student question competition. So if you're a student and you want to win some nice Polish Chemical Society gadgets, please ask questions. We'll choose the best question after the semester. Please remember to introduce yourself or use the full name in your Zoom profile so we can know who you are. Okay. The second question thing is I remind everyone about the Polish NMR meeting, which will be on 5th of December this year in Warsaw. The event is free to attend. And the registration deadline is in 2 weeks. So if you want to join us in Warsaw, please register soon, let's say. Okay. And we also have the information from Poznań NMR Society, let's say. So they are organizing Poznań NMR meeting in the middle of next month. So if you're interested in what's going on in Poznań NMR community, please register. I think it will be a great event. So with that said, we'll start with Sylwia Jopa talk. So Sylwia is from the Center of New Technologies, University of Warsaw, and she will give us a talk, a sample shifting split inversion recovery approach for quantitative NMR measurements. So I'm stopping the sharing, and the screen is yours, Sylwia.
Okay. Thank you, Mateusz, for very nice introduction. Okay, and
yes, we can see the screen.
Yes. Okay.
Yes. Yeah.
Great. Okay. So hello, everyone. My name is Sylwia Jopa, and today I want to tell you about a simple technical trick for reduced measurement time for the T1 time determination experiment, which is based on division the sequences into separate elements and apply them to different areas of the sample, and which can still give us some quantitative results in low field NMR benchtop magnet. Okay, so starting from some basic information about the NMR, on the Eurolab website, we can find some document named Guide to NMR Methodology, Development and Validation, Part 1, Identification and Quantification, which containing guidelines for NMR measurements. And in the chapter of on acquisition parameters, we can find some information about relaxation time. And it says that in quantitative NMR, the spin lattice relaxation time, T1, has to be considered. As we know, T1 is different from each signal of every compound and can also vary depending on the matrix, so like pH and the solvent. And to be on the safe side, the sum of the relaxation delay and the acquisition time should expand 5 times the highest T1 value of all evaluated signals. So theoretically, the factor 5 will lead up to 99% of the maximum signal intensity, and the factor 7 will lead up to 99.9%. Okay, so that's a gold standard of measurements that we are all familiar with and which we must respect if we want to perform some NMR measurements, especially quantitative NMR measurements. If relaxation is incompleted, the signals are underestimated and the quantification became biased. So that's why it's so important to know the value of the T1 parameters. And there are many different sequences used for this purpose, but the most popular one is inversion recovery, which use a 180-degree pulse followed by the variable period delay, and then a 90-degree pulse. We must repeat these sequences many times for different value of period delay to obtain a data set. And by observing how the signal's intensity changes with time, we can fit a curve and determine the compound's relaxation time. So great, but for the samples with a long T1 time says from 8 to 50 seconds. Sometimes for carbon experiments is even 40 to 60 seconds. This means that each experiment can take lots of time, sometimes hours. And particularly in the case of T1 time determination experiments, it is necessary to repeat the sequences many times for different period delays value and also take into account the appropriate time intervals for spin relaxation. So most of the time of our measurements is going for a weighting and not actually for collecting some data. And that's why we propose a completely new and very simple approach called SAR-SWAP. It's an acronym from Split Inversion Recovery, Swiping Apart for Polarization Enhancement. And the idea is to split the inversion recovery pulse sequences and apply its fragment to a different sample areas. And in this way, by using different areas of the sample, we can perform the experiment more than once without waiting for spin relaxation, and it's allow us to collect data faster while maintaining its quantitative characters. So we have two elements. The first, increasing the numbers of area of measurements, and the splitting sequences and adapted it to measurements in a different samples area. So let's start from multiplication the area of the sample. So how we do that? This is possible by SWAP. So not SAR-SWAP, only SWAP. And it is a solution developed in our group, in Krzysztof Kazimierczuk group by Augustin Romero. And it's a system consisting of a stepper motor and a test tube holder. It is placed on above the magnet, and it is responsible for removing the NMR tube vertically inside the spectrometer, as you can see on the video. And the connection between the stepper motor and the computer is made via Arduino controller, which you can see on the picture in the middle. And Augustin and Darek measured the area of a magnetic field homogeneity inside the 43 megahertz benchtop magnet in our laboratory, and determinate the area of a sample which is excited during the radio pulse. So thanks of these two pieces of information, they were able to identify 8 areas of the NMR tube that can be excited independently by moving the tube inside the magnet. And that's how SWAP avoid the long waiting time just by physically moving the sample between the scans. So here we have some examples, some results for proton and carbon experiments. On the left, we have some proton spectra. The relative integrals and the length waves are the same for the conventional method of measurements and the SWAP way of measurements. And at the same time, as you can see, the SNR value is higher in a SWAP method. And this happens because each scans excites the fresh, full relaxation part of the sample. So there is no partial saturation at the partial saturation at short repetition time. And the signal, of course, added coherently while the noise grows much more slowly. And on the right, we have some examples for carbon experiment results. And in the conventional experiment, the authors use 256 scans with 60 seconds repetition time. And in a SWAP way, they can use 2048 scans only with 7.5 seconds of repetition time. And both of these experiments took the same time. So here we also see that the peak area are still the same in both methods, and they match stoichiometry. And again, the SNR value is higher for SWAP method. So all of this was possible because time between exciting a given volume area move away and come back to it, it always at last 5 times T1. So now return to the SER fragment. So now again the SER sweep. In this case, we divided our sample into 4 zones for area. In our approach, the limiting factor is the length of time between the 180 and 90-degree pulse. And for short period delay times, shorter than the maximum fast movement of the sample, we use a traditional inversion recovery experiment without division. And this is the first cycle, where we use just a sweep wave of measurements, as which I described before, and but in the case of transition to the longer period delay values, longer where the maximum fast exit and return to the same volume, same area, we use split sequences. So then at first each zones is treated with inversion pulse, and then after the period delay time, there is a return to the appropriate zone and initiation of a 90-degree pulse and of course fit measurement. And therefore the total cycle time depends of mashing movement and signal acquisition rather than a long relaxation delay. So here's our results. So SER sweep experiment conducting on a 2 milliliter column of formic acid sample. This is the formic acid in deuterium water, I think 20 millimole concentration it was. And the experiment were repeated 5 times, and then based on them, we determined the error intervals. So the SER sweep experiment is almost 6 times faster, and the measured T1 value differs by only 10% above, something like that. And the T1 values from SER sweep and from the standard inversion recovery are within normal experimental errors. Part of the small difference comes from communication delays between the spectrometer and the separator motor. And as we can see, SER sweep gave us a clear exponential recovery curve, which gave us the valid T1 values and the related relaxation corrections. Overall, the method is strong enough for routine T1 calibration in quantitative work. So in our test, in this example, we of course use the simplest movement patterns. We can change the sample volume in order from 1 to 4 and repeat the cycle. And of course, we can imagine that for more advanced, more exotic movement patterns, they can also optimize the process of measurement even further. Okay, so for a little summary, in conventional stationarity NMR, long T1 values cause long delays between scans, which makes quantitative NMR impractical. Swipe allows the use of different sections of the sample, which shorter the measurement time. At the same time, a larger number of acquired scans increase the SNR. By moving the sample, full magnetization is achieved for each scans, allowing repetition time to be reduced without compromising accuracy. And the SER sweep shorts T1 measurements while maintaining quantitative accuracy. And this is possible because sweep returns to the excited sample volume, taking into account a specific period delay value and the relaxation time of each volume. So that's it for me. Our research was funded by the NCN Opus 23 grant project, and thank you very much for your attention.
Thank you very much, Sylwia. We have time for, I think, one or maybe two questions. So if anyone wants to ask questions, please turn on your microphone and camera. Oh, I see already Karolina Dydak wants to ask question. Yes, please, Karolina.
Hi, Sylwia. Can you hear me well?
Yes, perfect.
Okay, so thank you for your presentation. It was really nice. I have just one question. So for this splitted inversion recovery method, do you need the same volume of the sample like for the standard one, or more or less?
We just based on that yes. Okay, I now I understand. Okay, yes, we just need more than standard volume because we just need to move the sample. Yeah, so as longer column of the sample as possible is better for us. So here we have some examples for 10 liter column of the sample, and they gave us the more areas which we can achieve independently. Yes, so yeah. For this measurement, we just need to use longer tubes, NMR tubes, and the highest column of a sample.
Okay, thank you. I understand.
Okay, I think for the interest of time, we need to switch to the next speaker. So our next speaker would be Professor Szymon Pustelny from Marian Smoluchowski Institute of Physics, Jagiellonian University in Kraków. And he will give us a talk titled Nuclear Magnetic Resonance at Zero and Ultra-Low Magnetic Fields, a novel Swiss Army knife for physics, chemistry, and biology. So thank you very much, Professor Pustelny, for joining us, and the screen is yours.
Thank you very much. And let me indeed start with thanking Dr. Urbańczyk for having me, because I have to say I'm an outsider to the field. So although I'm working on nuclear magnetic resonance for quite some time, I've never got a real training in NMR as it is. So I'm very thankful for this opportunity. And I also would like to say that this is not that new anymore, but still relatively fresh in the field of NMR discipline. So I'll be talking about different aspects of this method. And if you have questions at any time, please do not hesitate to jump in and to ask me questions, because this way we may better understand what's happening. So as I mentioned, zero field NMR is, or what we call zero and ultra low field nuclear magnetic resonance, we'll call it ZUF NMR, is a relatively new field in NMR community. So I'll start with talking a little bit on why this might be interesting. So I'll talk about motivation, and I will talk about what it really is, what is really nuclear magnetic resonance, and how we can use it for various things. So we'll talk about some applications. In particular, I will talk a little bit about biochemistry, and then I will talk about physical applications, and then maybe finish with some conclusions. So in this community, this is actually not necessary to say that NMR is an interesting and important discipline across sciences and across technology. And there's two main applications: is spectroscopy, where we can gain a lot of information about molecular structure, arrangement, strength and orientation of bonds, and various informations which are extremely important for chemical sciences, but also for some other sciences and applications, for example, food industry or pharmacy or agriculture. And then, of course, at the other end of the application of NMR is magnetic resonance imaging, which is this technique which allows us to observe soft tissues in human body, and because of that, it gives us a very important medical diagnostic tool for investigations. And there's no surprise that because of this application, the NMR market is nearly constantly increasing over the past decades, and this is happening that probably a few billion US dollar a year is what is the NMR market worth these days. But when you think about NMR, you almost imminently think about strong magnetic fields, right? You always have in mind your experiments where you have a strong magnet. You think about the experiments where you have a strong magnet for magnetic resonance imaging, and there is a very good motivation to do so. And this motivation to do so is actually twofold, right? The one motivation is that, I mean, the higher your signal is, actually the better sensitivity of your measurement is. So you would like to have as strong and at the same time as homogeneous as possible the field as possible, because you will get a better spectral resolution of your signal. Then the other reason for a strong signal is a chemical and analytical capabilities of the technique. Because of the chemical shift, the line positions for different for the same nucleus in a different compound is shifting to different positions. And if you want to observe this, you actually would have to have a field that is stronger, so that the splitting due to chemical shift is larger than the line width of the resonance itself, so that you can say something about it. But this strong magnetic field comes at the cost, and this cost is actually the necessity of using very strong magnets, and in particular superconducting magnets. So if we are talking about superconducting magnets to generate this few Tesla fields, we talk about several problems. We talk about the problems of price, because if you want to do it, you have to keep it in cryogenic. And this is expensive. And then on the other hand, if you want to do it, you have to keep it in cryogenic. And maintaining cryogenic is not super obvious, so it also poses some challenges. But there are also some other challenges which are associated with limited applicability of this thing. Because, for example, if you want to do MRI of people, you are not able to do it to people with pacemakers, with shrapnels, if we are talking about war conditions, or implants or magnetic implants. And of course, if we are talking about magnetic objects close by, we'll face a lot of challenges with susceptibility problems and shielding maybe to some extent. So these particular reasons cause that from the very beginning, people start thinking about relatively low field NMR. And even founding fathers, people like Russell Marian and Martin Packard, thought about doing in an Earth magnetic field. So there's a significant area of doing NMR in Earth magnetic field, even today. But then in the 1980s, late Alex Pine at UC Berkeley, was thinking about what's going to happen if we will do this at zero field. And of course, at the time, it was not really possible. So the idea he came about was maybe you can have your sample and you can shuttle it between the high field region and the low field region, and then measure that, let it evolve in zero field, and then bring it back to the high field region for measurement. And then in early 2000s, people like John Clark, this is this year's Nobel Prize laureate, and I have this. You probably saw this picture of him when they were announcing it. I have to say I have this picture for a couple of years now in here. So John Clark was applying squid magnetometers for NMR signal detection at zero field, and then my former PhD supervisor, Professor Dmitry Budker at UC Berkeley, and some colleagues start to think about the same applications, but removing or replacing squid magnetometers with optical magnetometers for measuring the signals. So this is somehow how I get to involved in this business, and I will tell you a little bit more about it soon. But what it even means, zero and ultra low field, what it means conventional, what it means low field, and what it actually means zero field. So this is very difficult to give you some precise number where conventional NMR begins or low field NMR begins, but you can quantify it in a following manner. You can say that conventional NMR is an NMR in which chemical shift of the levels is significantly larger or larger than the line width of the observed resonances. So this is the range of fields, which I would say would be probably slightly around and above 1 Tesla field, where this is happening. Then probably somewhere around 100 millitesla for many compounds, the chemical shift is comparable with the line width of what you measured, or even smaller. And then I would say this is the place where still Zeeman interaction dominates any other interaction in the system, but we are not observing chemical shift, and I will call this range low field NMR. And then you can go down with your magnetic field still, and somewhere below or comparable and below Earth magnetic field, you'll find that Zeeman interaction is not a dominant interaction anymore. It's actually the Zeeman interaction is comparable with line width of what you're observing, or maybe smaller than some other interactions in a molecule. And then that's what I would call zero and ultra-low nuclear magnetic resonance. This is the place where actually Zeeman interaction either not exists at all, or it's just a small perturbation to some other interactions in the molecule, which I will discuss in a moment. So we are talking about zero field NMR range, and we are talking about people who are interested in this, but for some reason, this was not blooming over and somehow not very popular. And the reason for that is twofold. It's either fundamental or technical in nature, and I'll try to explain why that existed and what we can do about it. Well, the first reason for a strong magnetic field in NMR is actually thermal polarization. Most of our experiments that we are performing is actually performed in a strong magnetic field. And then in a strong magnetic field, the levels are being split, the nuclear levels are being split. And because of the Boltzmann distribution, there is an excess of a population in a given energy state over the population in a different energy state. At room temperature, this actually can be shown that it scales more or less linearly with the magnetic field. And because the thermal energy is so much larger than the Zeeman splitting, that you can say that there is a little bit of the difference. And in fact, even in the strongest magnet these days, the excess of one polarization over the other polarization, so one orientation over the other orientation, is on the order of 10 to minus 5-ish. So I would say 10 to minus 5, 10 to minus 4 in the strongest systems, which means that typically 1 in 10,000 or maybe 100,000 nuclei is being polarized in this manner. So there is a particular reason you want to go to higher field to get better polarization. However, if you go to zero field, there is no Zeeman splitting per se. So there is no the ability of thermal polarization, and you have to somehow solve this problem. So how do you solve the problem of polarization in ZULF NMR? Okay, one problem is you can do remote pre-polarization. So what you can do in this business, you can take your sample, you can place it in a strong magnetic field, and then mechanically you can bring it back to the zero field region when it's being measured. So you can ask ourselves a question. So, okay, what are you winning? I mean, you have to use a strong magnet, which is true. However, which is very important in this business, is that this pre-polarization field have to be strong, and you can have a permanent magnet these days, or an arrangement of permanent magnets that gives you something like 2 Tesla field. But what is the most important part is that for the polarization stage, this field doesn't have to be very homogeneous. So the technical challenge that you have to face every time you're working in high field NMR systems is that you don't have to shim this system. You can have a strong field, 2 Tesla field, you can polarize it, and you can build your magnet for less than 1,000 euros, maybe something on the order of 500 euros, and you can get a signal, you can get a field that is roughly 2 Tesla. However, even with this arrangement, you still suffer the problem of low polarization. So maybe you can be smarter in this business and maybe you can do something else. And of course, there is a huge branch these days of NMR, which is associated with hyperpolarization. So you can, in principle, polarize something else very efficiently and then transfer this polarization from whatever you polarize to your nuclei. And this is what is being done with dynamic nuclear polarization. You polarize your electrons and then you transfer the polarization from electrons to your protons or to your nuclei in general. But this is being done also in a very strong magnetic field. So the question is, can you do something in a much weaker field, or maybe potentially zero field? And in fact, there are hyperpolarization methods. For gases, we can talk about spin exchange optical pumping, which can be used to polarize gases. Or what you can do is that you can do parahydrogen-induced polarization. And in fact, in this movie that you are seeing, there is a little tube that are being introduced into the system, and there is a parahydrogen being bubbled through the sample. And with this manner, you can polarize your sample at a level of maybe even a few tenths of percent if you have your system. However, this is the technique which involves some chemistry. I mean, you have to do it. Either you have to do some hydrogenation relation between your parahydrogen and reaction between your parahydrogen and your sample of interest, or you have to have a substrate in which this is reversibly exchanged between the surface. So we have to do some chemistry here to improve this thing. So this is the first thing, but the bottom line here is that you can now generate a quite efficient polarization, even not using strong magnets. So you go around the first problem of polarization. Then the second source of high field in NMR is detection. In conventional manner, we're using pickup coils, and we are using Faraday induction law, which says that what you are measuring, what you're interested in, is you're interested in the changes of the flux of the magnetic field. So even in a given flux, if your flux is changing faster, you have more signals in your system. So what you are doing, you're bringing it to stronger and stronger and stronger fields, because the Larmor precession of your spins is increasing linearly with the strength of the magnetic field, and you get a better sensitivity. However, this is only true, and this is only working if you have a strong field. If you have a weaker field, the situation is becoming much more involved, right? You can go down with the frequency, as is shown in this plot, and then the lower your frequency is, the lower the sensitivity of your system is. And these are simulations done a couple of years back by my colleagues, who shows that in a range maybe going to a megahertz, you have a relatively insensitive coils, which means that you can look into alternative schemes of detecting these signals. In particular, superconducting magnetometers, the ones that John Clark got the Nobel Prize for, is actually very sensitive in ranges up to maybe a megahertz, and the sensitivity could be on the order of a few femtotesla, which means that we are having a relatively sensitive technique. But and another alternative is something that I was working on for many, many years, which is optical magnetometry. Optical magnetometry is this technique in which you illuminate a sample, which is typically alkali metal vapor, for example, and you look at the properties of light that traverses the sample. And what happens is that if this sample is subjected to the magnetic field, the properties of the light are changing. The intensity is changing, or the polarization state is changing. And if you are able to detect this change, you can measure the magnetic field. And in fact, the simple idea allows you to measure various fields to a sensitivity of some femtotesla per root hertz, or if you are measuring oscillating magnetic field, maybe smaller than zero field sensitivity, in a bandwidth of maybe 100, maybe hertz, maybe a kilohertz. So these devices are actually these days commercially available. You can buy them for maybe $10,000, and they give you below femtotesla per root hertz sensitivity and a bandwidth of 1 kilohertz. So this is a sample. These are approaches which can be used in this system. So this way, we can get rid of the magnetic field at the polarization state. We can get rid of the strong necessity for the magnetic field at the detection stage. But if that would be for it, that would be the end of the story, because as I mentioned before, the most important, or that one of the two most important aspects of NMR, it's analytical capabilities. So because of the chemical shift, because of the diamagnetic shielding of the nucleus by electrons surrounding the nucleus, you can get a shift of a specific type of nuclei sitting in a given given molecule. So if you are able to detect this shift, you can say what your molecule is. For example, you can use it for fingerprinting, or you can get this. You can learn something about interaction inside the molecule. So if you go down with the magnetic field, this thing disappears and you are not able to detect it. So you cannot base your analytical capabilities on this particular example. So what you have to do is that you have to now look into the molecules more carefully and identify what's happening there. Look into the Hamiltonian of the system and see what are happening there. And of course, if you are talking about a standard system, NMR system, which has a couple of Tesla magnets, the dominant interaction is a Zeeman interaction. So this is the strongest interaction. However, if you go to zero field, this signal, which is on the order of hundreds of megahertz, disappears. Then, if you look into the molecule, and this molecule is having spins with a nuclei with spins larger than 1/2, you will find that there is an interaction of electric field gradient with a quadrupolar moment of the molecules, and this gives you a very strong signal. So this is what is being used in NQR, nuclear quadrupole resonance, to identify some systems. But if you choose molecules that only contains 1/2 nuclei, this disappears again. Then, of course, you have your dipole-dipole interaction. So your molecules, your nuclei in the molecules are having different magnetic moments, and they can talk to one another, that can affect one another, that can interact. However, if you choose isotropic liquids as your sample, this is tumbling a lot, and you will find that this contribution is also disappearing. So what you end up with is this scalar J coupling interaction in the system that is on the order of from a few hertz to maybe 1 kilohertz, or more typically 200 hertz in the system. So this is the only interaction that survives in the molecule. This interaction is a nucleus to nucleus interaction that is mediated by the electron. So one nucleus is polarizing electron, and because the cloud electron is being shared by many sites in the molecule, it can repolarize the other molecule, and these two can talk to one another. So this is the Hamiltonian we are talking about. And this interaction is typically 6 to 8 orders of magnitude weaker than the Zeeman interaction in high field NMR. It's sometimes being investigated, of course, but in zero field, this coupling is actually the only surviving coupling in the system. So this is gonna be the signal, the interaction that has a strength of a few tenths or a few hundred hertz, which is ideally suited bandwidth-wise for optical magnetometers. So we can now use these optical magnetometers to search the signal. So these are what it means, that now is that now we can build a system that consists all of these elements. So we are typically using a liquid samples in our measurements. These are samples of roughly 100 microliter samples, which are placed in typical NMR tubes. Sometimes we can we degas the samples. And then we place the samples either in a magnetic field of a strong permanent magnet, or we can also use a hyperpolarization using parahydrogen. We built a parahydrogen station in our lab, so we can use it. In a business. Depending on which solution are you using, you can either shuttle the sample between permanent magnet and the zero field region inside here, or you can place it already inside and then bubble it even inside the shield. So when the shield is coming when the sample is going into the system inside the zero field region, it's going through the cylindric layers. These are the layers made of mu metal, which works as a passive attenuation of the magnetic field. So typically the system is being shot from all directions, so we don't see anything on this side. It's only being shown for presentation purposes, but the field is reduced to some below nanotesla level inside of the shield. We also have some magnetic field coils inside to generate pulses, to manipulate with the levels. And then somewhere here, which is very difficult to see, is an optical magnetometer that measures our signal. So we bring our sample from a very strong field of a permanent magnet, for example, inside the magnetic shield, where magnetometer measure the free induction decay. And this is like a real-time experiment. We have a sample inside this tube right now. This blue thing is a magnet. There is a solenoid going down. The sample is being dropped down. This is the magnetic shield that I talked about. And this is what we are seeing. You can see that inside there is a tube that is sitting next to the magnetometer. It measures magnetization. It's being pulled up. And now this is a real time that we are seeing from our experiment. We can zoom on this 220 Hertz signal, and this is actually a signal for formic acid that we've just measured in our experiment. This is a single shot measurement in this system. So what we are seeing? Well, we are seeing a signal that we call free induction decay, which is of course not induction, but it will be free magnetization decay. So we are measuring magnetization. We are seeing a lot of oscillations, and the signal is decaying, So if you Fourier transform the signal, you can find a huge zoo of different lines. This is a relatively complex system that we are using, and you are seeing there's a whole zoo of lines at low frequencies around 10 Hertz, and then all the way up to the 70 Hertz. What is important in this business is that this is a unique information about the molecule. So it can be used for chemical fingerprinting, because now each molecule, because of a different structure, because of the different bonding strengths and so on and so forth, is having this line sitting in different positions. So you can do fingerprinting using this one. These lines are actually extremely narrow because of the absolute inhomogeneity of the magnetic field, which is completely negligible in this field. We are operating, in fact, in zero field, or very close to zero field. Your T1 time is on the order and sometimes shorter than T2 time in your business. So your transverse relaxation and your longitudinal relaxation are typically the same. And then you have an access in a single shot, because we are seeing different interactions. You don't have to be tuned to the specific nuclei in your business. You can measure all the nuclei. You can measure protons, you can measure C13, you can measure N15, and so on and so forth. You get a full information. And last but not least, and I will come back to this one, because it's low field, it can be actually turned into a desktop NMR system, which I will talk about a little bit toward the end. So what is exciting for me in this business is actually that this simple system, which is molecular system, reminds me know from atomic physics, which is my background. So I know that we have two spins, they can add parallel or anti-parallel, they form energy level structures. I can see this energy level structure, I can calculate this energy level structures, I can calculate the splitting between the energy level structures, I can even draw some information about possible selection rules. So which level I can directly access with my measurement, or which I can access with using some electromagnetic field by coupling these levels. So this is extremely interesting because now I can, on paper, show the position of the lines, and these lines are extremely long-lived. So in particular, you see an example that I'm showing at this plot that is a 3-metal phosphate and 3-methyl phosphide, which are very similar molecules, but the molecules that are having a slightly different J couplings between this phosphorus here and this protons here. And if you count it very carefully and you say that there's like 3 of these groups, you will find that you will have 5 potential lines at 1J, 2J, 3J, 4J, and 5J, which are being very clearly visible here at 10, 20, 30, 40, and 50 hertz. And also the lines are extremely narrow, so you can see the shift of the lines. So now you can also say which compound are we talking about. And which is also extremely important because of that simplicity, we can calculate the positions of the lines. We can easily calculate the spectra of the simple molecule and say which lines should be there and what are the amplitudes of the lines, because not only positions but also the amplitudes of the line can be calculated and can be extracted from these measurements, and you see this is something that is happening. Of course, when you talk about molecules, you want to talk about some maybe even more complex molecules. And then you can do, once again, something that you know very well, and I know from slightly different perspectives from atomic physics. I can do a perturbation theory. I can assume one interaction is strong and there is a perturbation. I can measure this perturbation. I can calculate the splitting of the lines, the shifting of the lines, and I can reconstruct them. And this is exactly the situation I'm showing here. So I'm now showing a signal which is from dimethyl methylphosphonate, and you find that there is a bunch of lines at low frequencies, at higher frequencies. The positions of the lines are being determined. Some of them are split, some of them are being shifted also, and I can calculate it either based on some analytical tools, which is possible to some extent, or numerically diagonalizing the matrix describing the system. So now I have a tool that allows me to determine the position of the lines, the amplitude of the lines, and say something spectroscopically about the lines. So let me give you maybe 2 examples of the applications, or maybe 2.5 examples of applications of the Zulf NMR technique. One will be associated with chemical and biochemical analysis. The other one will be associated with some physical approaches. So as we discussed, we are able to calculate the position of the lines. We are able to determine the position of the lines. And we said that because of the length of the lines, we are very sensitive to the changes in the structure of the molecules. So here you see a couple of molecules that are being measured in my lab, and you see when you change this structure of the molecules, the position of the line, the length of the line, the structure of the line is changing, and you can say something very deterministically about the lines. So you can see how these lines are being how this spectra is being changed. You can measure it, and you can also simulate it. But what is also interesting is that not only you can change the structure of the molecule, but you can also detect the changing of the bonding position of the molecule. So for example, if you take it out spectra 4 or 5 or 6 or 7, you see that the structure is being slightly modified. We are bonded in a different place, but this is being clearly visible in the spectra that we are seeing. So what I'm trying to say right now is that we have a very nice tool to perform chemical fingerprinting, chemical analysis, to perform spectroscopy using this technique. So ZULF NMR is a very nice system to perform spectroscopy. The question you may ask is that, is it good for everything, or is the signal to noise ratio good enough? And this is a very fair question, and I would say two important things. The first one is that when you do the thermal polarization of your system and you want to measure your system, you have to have a heteronuclear coupling, J coupling in your molecule. So you have to have two different types of molecules with non-zero spin that you can measure and investigate in this business. So this is typically not so easy because you have to change sometimes you have to label your molecules, like consider an example, which might be expensive and not always possible, but this is necessary tool if you want to measure your spectra. So, for example, we are typically labeling our samples like formic acid or methanol or ethanol in our measurement, or other measurements in the system. However, you can a little bit go around this problem by using hyperpolarization. If you use a hyperpolarization, you automatically boost your signal quite significantly. So you can use this technique to increase your signal to noise ratio, or even in some cases to observe the signals that you are interested in. So spectroscopy using ZULF NMR is one aspect of this chemical or biochemical application of the system. The other one goes a little bit along the lines of the previous talk when we heard about relaxometry. So even in ZULF NMR relaxometry, you can start to measure your signals. And we performed some very simple measurements in the past. We have an aqueous solution of glucose, and we measured relaxation time and amplitude of our signal versus different storage times, and we observed that depending on the glucose concentration, our relaxation time, longitudinal relaxation time, was being shortened in the system. So, and the shortening is being somehow correlated with a glucose concentration in the system. So with this, you can also look into NMR silent compounds like glucose by observing the polarization of your protons in the system. So this shows you some interesting applications of the ZULF NMR relaxometry. But what interested us even more is to even extend it further. And what we did the measurements with the blood. So we took the blood, human blood, and we performed measurements with ZULF NMR. Typically, blood is a very difficult to work with because it contains cells, it contains iron, and of course it contains oxygen, and of course this affects your relaxation time. But what we did show in our measurements is that we can measure the signals. We observe ZULF NMR signals, and the ZULF NMR signals for whole blood, and then the plasma, which is a fraction of the centrifuge blood, is different. And we observed that there is also some dependence of this blood signal versus the relaxation time. These two signals were measured for the very first time in ZULF NMR. This is not very typical NMR measurement, but it shows that it can be used for analysis of the system. We also try to detect some dispersion of a relaxation time in the system because in principle relaxometry will give you an access to the processes that occurs in the molecules at a time scale of microseconds or milliseconds, which is typically not accessible for high field NMR. But to be honest, we haven't seen a clear view of that something is happening here. This is apart from the fact that plasma is having slightly longer relaxation time, maybe by 1/3 than the whole blood relaxation time, and we associated with some cell structures that are still being there. Anyhow, it looks like there might be some little dependence, but in principle, this opens some avenues for investigation of biological liquids using NMR and maybe storing some and deriving some information from this one. So this is this part that talks about the biochemical application, something that I really do not know much, and I'll be happy to talk some more about this, in particular to you who are interested in biology and chemistry, because I think this technique has a very strong potential in biochemical sciences. However, I also use it for searching for physics beyond the standard model. So not to talk too much, I would just say that there are two theories in physics that are actually describing and explaining how our interaction, how our universe is being governed. So we know that there are three fundamental interactions, which is electromagnetic interaction, which is strong interaction and weak interaction, and this is being enclosed in what we call the standard model. And on the other side, there's a gravity that is being explained with general relativity. This theoretical framework works really nicely, but they have some very fundamental flaw. One of this theory is what we call the quantum field theory. The other one is a classical field theory. So they are not compatible. These two theories cannot be merged into one theory that explains everything. And we hope that there is a theory of everything that explains all the interactions. So people for a long time look for some alternative gravitational theory. And in particular, there's one theory that is called quantum gravity, or some group of theories where people think that the same quantization, the same quanta that is being used to explain standard model interactions are actually being used for gravity. The problem is that this is very weak interactions, and nobody really measured these interactions despite many attempts. And we also make an attempt to measure this because some of the theoretical models says that gravity can couple to your spins. This interaction is very, very strong, but if it does, it will be some link that there is quantum gravity in a field. So what we are doing right now is that we are performing an experiment in which we are looking at a precession of spins in a magnetic field in two different situations. One in which your magnetic field is parallel with gravity, and one in which they are anti-parallel in the gravity. And if you find any difference in the precession frequency, that could be associated with the gravity. But of course, I mean, the most important interaction is the gravity. So the question is how well you can reverse your magnetic field, because if you don't reverse this ideally, you cannot actually measure gravity. You will measure that your magnetic field in one direction and the opposite direction was not equal. So we are aware of this one. So we built something that is being called a liquid state Zulf-NMR comagnetometer, where we look not at a one compound, or maybe we looked at a one compound, but at these two different frequencies. I told you that there are these energy structures that manifest at different frequencies. So now we are looking at the frequencies as 1J and 2J in the system. It's in the system. I think this is acetonitrile at this point. And we compare the splittings because we know how the splittings should be in this business. And if we can compare the splittings, we can actually get rid of the sensitivity to the magnetic field to the first order. So we did this measurement. We see how well we can measure the splitting of the lines. This is some statistic in one direction and some statistic in the other direction. And actually what we did, we estimate the limit. We haven't seen any deviations from what it really is, if there is any splitting. So these are equal. So we determine that if there is any couplings of gravity to spins, it cannot be smaller than this number. And this is very new thing that we are actually doing the thing, exploring in my lab. Okay, so this brings me to the conclusion of this talk. So what I tried to tell you is that I tried to show you that we are having this new tool, which is zero field NMR, which has very intriguing and very interesting properties that can be used. And they can be used for spectroscopy. I would like to go toward metabolites, sugars, amino acids, and things like that, because I think there might be a lot of interesting applications there. There's also a relaxometry of biofluids. I was talking about blood, but we can talk about urine. We can talk about the different things that can be investigated and then can be probably correlated with some chemical or biochemical processes or maybe anomalies in your blood. So this is something that that are being explored. And what I would like to stress here is that this is not an area of my expertise. So if there are people in the audience who would like to talk about it and who would like to explore options, I'm absolutely open for exploring these biochemical applications. We have a system that sits in my lab and that can be explored for any of this. The other part of this thing is actually physics. And I talked to you about searching for physics beyond the standard model. We talk about gravity. There are some different exotic interaction that we can look for. But we are also performing quantum state engineering right at this point, where we are applying pulses to magnetic field and we manipulate the state of our system. And we can also reconstruct the state of our system of the in our molecule. And what is really beautiful about NMR molecules is that the lifetime of the systems is being extremely long in comparison to some lifetimes in other systems. So we are also exploring this. And last but not least, I think that this approach is having a very interesting possibility. This actually can be miniaturized, and my company these days is working on the construction of portable Zulf NMR system, miniaturized system, and I think this system could be a desktop system. So we've heard about the bench top NMR system, which is probably 300 kilogram heavy. I think we can build something that is being complementary to the technique that can weigh maybe 10 kilograms and being actually the size of the maybe 30 by 50 by 30 centimeters. So it could be really a desktop system in which you can explore this working in your office. So with this, I would like to acknowledge some of my colleagues, some of the people who did a lot of work. We have a lot of collaborators, particularly in Mainz. We have collaborators in Southampton, where we're collaborating with Malcolm Levitt and his students, and also Simon Duckett, who is like the best probably expert in power hydrogen-induced polarization in the world, who helped us a lot in developing some of the schemes that we are talking about. So with this, I would very much like to thank you for your attention.
Thank you very much for fantastic talk. We are open for the discussion. I encourage especially students to ask. We have a competition. And if you want to ask questions, please turn on your microphone and if possibly camera and start asking. Anyone interested? Oh, Krzysztof.
Well, hello. Yeah, I'm not a student, but I have a question. Maybe I missed something, but did you mention how sensitive the method is to magnetic field disturbances? I wonder how is it compared to high field NMR? Is it more of a problem or less? How is it?
Okay, so the idea here is that we are operating either at truly zero field. So we are going all the way to zero, and we are talking about magnetic field that are being first passively attenuated to something to the nanotesla level. And then we are even going with some further techniques to maybe something at the picotesla level. So the first thing is that we are not having any magnetic field, and you see the structure that we talked about. Then the other thing is that now, which I didn't really talk much about, is that you can take this system, which is dominated by the J coupling, and then you can apply a little bit of a magnetic field with this coil that sits inside. So something on the order of maybe some tenths, maybe hundreds, maybe a microtesla in this business. And then you can see the structure, how it splits, what you can do. You can address some of the transitions. But to directly answer your question is that we are not being worried with the magnetic, in the first order, we are not being worried with the magnetic field whatsoever because we do not have magnetic field, or our magnetic field is extremely weak, and the pre-polarizing system is sitting outside of this magnetic field region, so it's being shielded with this passive attenuation, so you are not seeing any of this leaking into the inside the magnetic field. So that's the answer to your question.
Okay, thank you.
Any other questions? Okay, so maybe I'll ask one question. So you showed that you can quite easily simulate the spectra of different molecules. Were there any attempts to, for example, analyze the whole mixture with Zulf, or you only work with single molecules usually?
This is a good question. We have mixtures. I mean, we did have different mixtures. We did have different systems. We didn't really go all the way to some very complex mixtures. This is something that we would like to do. We even claim at some point that we'll be able to do chemical fingerprinting, analyzing the molecules, use some AI systems and things like that. But of course, life is being very interesting. So at the way towards the doing it, we found another topic which interested us even more. So it's still on the table. So in principle, first of all, in principle, it's doable. Then the question is, if you know what the mixture is, establishing the ratio between the mixtures, this is still doable. But it's not being as beautiful as we hoped. It's going to be automatic, where you put a mixture, you measure something, and you extract the information about what's indeed being there. So with this, not really, no.
Okay, thank you. Any other questions? Students are really encouraged.
Maybe I have a little question.
Okay.
Maybe I missed something or didn't understand it correctly, but did you say that only heteronuclear J couplings are possible to measure, that you have to really have different nuclei, and then you can see the splittings? Or is
it is indeed true. So we have to have a heteronuclear coupling as the first coupling in the system. So there has to be C13, for example, and hydrogen. And then on the top of this one, we can measure homonuclear coupling. So the homonuclear coupling will be addition to this model. And the reason for that is that the evolution of this thing assumes that these two compounds evolve at slightly different frequencies. I mean, at different frequencies in a given magnetic field, and different nuclei are having different gyromagnetic ratios. So there you see some sort of a beating between these two compounds. And again, if you want to look at a homonuclear coupling, it's possible, but on the top of something else. So this is actually some sort of a limitation if you want to talk about the technique.
Okay. Thank you.
Anyone else? Just give it a moment.
I have some question about simulation with spectrum with decouplings. What about this method? Some word, some.
Maybe here.
Oh, yes.
So the easiest way to answer this question, you can do it brute force approach. Namely, you write your Hamiltonian for a number of spins that you are considering. You put the coupling constants between different places, different nuclei in your system, and then you simply, for example, numerically diagonalize this Hamiltonian, finding the eigenfrequencies and eigenstates. So this is the way you can do it, and then by hand, and this is a little bit of a cheating, by hand you are putting a relaxation into this business. So when you know what they are, you sort of guess what the relaxation rates are to more or less mimic what you're seeing experimentally. But the position and amplitude of the lines can be determined. You can do it in an easy way as I said, you can diagonalize this matrix. If this is a simple system, you can diagonalize this matrix analytically, and then you know the position of the lines. This is actually what is happening here. We know what the structure is. We know that between these two, for example, there will be 1J. Between these two, there will be 2J in your system. So they will manifest at different point. And then if there is a weak perturbation on the top of this one, you can perform perturbation theory, and then again measure it analytically. But we showed recently, and I forgot to say that we quite recently wrote a review paper, which I cannot find right now, this year, which is this one, which describes many aspects of this thing, and in particular, they discuss to which extent the analytical approach is well suited and can be used, and to which extent you have to go toward the numerical simulations to explain this system. So that's how we're doing it.
Yes, but my question was considered exactly the method of calculation with spectrum with couplings constants.
For example, it's a numerical diagonalization of the interaction matrix.
Thank you very much. Very good lecture.
Thank you. If I may, I'm not sure if there are any more questions, but as I said, and I want to stress it, I'm not sure how much time I can stress it and how strongly, is that I'm not physicist. I'm a physicist myself. I'm not involved in biology. I'm definitely not involved in chemistry. So if you're having any questions, any discussions, I encourage you to look into the paper. But I will be happy to discuss, because we are having quite a unique apparatus, which I think can be used for interesting topics that I'm not aware of. So that's what I want to say. So please do not hesitate to contact me. I'll be happy to discuss more.
Okay, the last chance for asking questions. Okay. I think the questions are over now. So let's introduce the next seminar. Okay. So the next seminar will be in 2 weeks. We'll have 2 speakers as usual. So first student talk Karolina Dydak from Adam Mickiewicz University, and then we'll have the very first talk from the United States and from industry, Dr. Justyna Sikorska from Merck & Co. So see you in 2 weeks then. And thank you very much for speakers again. This was great talks. And yeah, thank you very much, everyone.
Bye.
Thank you very much.
Thanks.
Bye.
Bye. See you.
Bye.